Hello. This lesson continues the previous lesson on exponential function f of x equals to 2 to the power x that we have discussed in the previous video that it is a one-to-one function, right? It is an increasing function, its domain and range we have discussed. And what is more, as a one-to-one function, its inverse is log base 2x. It's log base 2x. We're about to do the graph. Before we do the graph, I wish to recall with you, right, to review that usually in any particular text, most of the textbook, they will introduce logarithm as in this form. Okay, they may use different symbols for in the place of omega or triangle, but this is the definition of logarithm. This is the definition of logarithm. So in our special case, when the base is 2, that's what we have. That's what we have. Okay, so according to this definition, right? And we're going to graph this function. We're going to graph this function. And what is that function? This function is log base 2x. We know it's the inverse function of 2 to the power x. And let's see what we got, right? We already know the domain and range as well. But it doesn't hurt that we're gonna have a further discussion from the other perspective, which is the definition of the common definition in the popular textbooks. Okay, so now the rule is F inverse. Okay, F inverse. It produces an output. That output is going to be log base 2x. Right? So any input you give me, we're going to produce an output, right? In our previous discussion, in the inverse function context, we have decided the domain is all positive numbers and the range is all real numbers, right? So let's take a look, right? Could it, well, why it cannot be 0? Why it cannot be 0? Right? We're going to bring the definition with us. So we're going to put it right beneath us so we can, have access to it. Now, suppose I have a -1 as input. Okay, -1 is the input. With this input, right? The input is -1 and the input is -1. The question is, what will be the output, right? Because if -1 is in the domain, it should have exactly one output for it. Suppose that exactly one output, we're going to call it triangle. Okay, by this definition, right? By this definition, in the place of omega is -1. So this should be -1. And 2 to the power of a triangle should equals to -1. Okay, so triangle is the number we're looking for. Triangle is the number we're looking for. What is it? What is it? In our earlier discussion, right? We know that 2 to the power of x is greater than 0 for all real numbers, for any x in the domain from -infinity to +infinity, right? That is a one-sentence statement about domain and range for 2 to the power x. In other words, 2 to the power x will never be 0 for any x it will never be negative. So this will never happen because 2 to the power of anything is always positive. Therefore, in this case, there's no solution for the triangle. So now let's recall the definition of function, right? The definition of function says a function is a rule that assigns each input in domain exactly one output in range, right? If -1 were an input, it should have exactly one output for it, but we don't have it. Therefore, okay, therefore, in this case, okay, for -1, by this rule of function, there is no output for it. As a result, -1 cannot be in the domain of log base 2x. So, and then the same reason applies for any negative number, right? How about 0? How about 0, right? So what if I have a 0 as the input? And the input is 0. What will happen? By definition, right? The place of omega is 0. So this is 0. So we need to find the triangle, a number that in the position of triangle, 2 to the power something that is equal to 0. Does this number exist? It doesn't, because for any real number power 2, it's going to make 2 to the power x positive. So this is always a positive. A positive number will never be 0. So in this case, there's no solution again. There's no solution again. So for the same argument, okay, exactly the same argument. Okay, so I'm just going to copy and paste. For the same argument, right? A function is a rule that assigns to each element in each input in domain exactly one output in range. And in the case for 0, by this rule of function, which is a log base 2x, there's no output for it. Therefore, 0 cannot be in the domain. And so from the other perspective, we can also see that the domain for log base 2 must be positive numbers only. Positive numbers only. It can be bigger than 0, like 0.001, 0.002. That's all fine. So let's get to the graph. Let's get to the graph. Okay, so we're going to see if the range is going to be from -infinity to +infinity. Okay, so now we have confirmed that the domain has to be positive numbers. Okay, or we can use another words. Say the domain, which is the input, right? This quantity is in the place of input, has to be positive, right? Now, we're going to work on the graph. Graph. Okay. For convenience, we're going to, make a table. Input, output. Input, output. Okay, the ordered pair. The input, we can only choose what? We can only choose numbers that are positive. We can only choose a positive number, right? We cannot choose 0, undefined as 0. But we can choose numbers that are a little bit larger than 0. And of course, we can choose numbers like 1, right? 2, 4, 8, right? Those are, powers of 2. We can also choose half, which is closer to 0. We can choose a quarter, right? So we can keep choosing. We can keep choosing, okay? I would like you guys to okay, getting closer and closer to 0, right? And another number that's even closer to 0, 1/8. We can keep going, right? 1/16. I'm going to leave 2 places that are blank, right? So let's work with some numbers and we apply the rule. The rule of the function, and don't forget, we have a definition next to us. So we can apply this definition when we need it, right? So let's start from easy number. Right? I think 1, 2, 4, 8 will be pretty easy, right? So we're going to apply the rule of the function. We're going to apply the rule of the function, just log base 2x, right? Log base 2x. When the input is 2, what will be the output? In other words, if the input is 2, right? What number power 2, right, should equal to 2? So that number is here, right? Of course, that number, the number power 2 equals to 2, that should be 1, right? So this equals to 1. So when input is 2, the output is 1. Okay? For 1, if input is 1, right? If this is 1, so what number power 2, right? What number in the place of triangle is what we want, right? So this is a triangle. This is the number we want. That's the output. So what number power 2 is going to equal to 1? 0. That's right. 0. Okay. And how about 4? Input is 4. And this is going to be 4. So omega place is 4. So what number power 2? What number power 2? What is this triangle to be? So that 2 to that triangle is 4. 2, right? Because 2 to the power 2 is 4. So we got another point. Input 4, output 2, input 1, output 0. We have one more number here. Okay, would you like to try it? What would that be? What would that be? Oops. Wrong place. 8, right? So raise omega place is 8. So what number power 2 equals to 8? 3. That's 3. Okay, I also want you to observe something else, right? 8 is 2 to the power 3, isn't it? Oops. So you may notice a log base 2. And if the omega place is 2 to the power 3, you just have to bring the power down, which is 3. Okay, so 8, 3. 4 is 2 squared. So log base 2 that base 2. The exponential part on the omega place is base 2 as well, 2 squared. So you just bring this 2 over here. 2 is 2 to the power of 1. So that equals to 1, right? So whenever these two number matches, these two base matches, right? One is log base, one the exponential base. When you have these matches, you can see how easy that is to figure out the answer, right? Input, output. Now, how about 1? 1 is 2 to the power of 0, right? So that rule still applies. Next was half. What happened if the input is half? The input is half. Right? What should that be? What if this is half? Right? This is half. What is half? What number power 2 give us half? Well, -1, right? So this should be -1. This is -1, right? So this answer is -1. And also you might notice that half is 2 to the power of what? -1. So when input is half, you may like to start plotting points. Okay, you may start plotting points. Actually, as a matter of fact, we're going to do one more and we're going to start plotting. Okay, so we're going to save these two and we'll do it later. And next one, if the input is a quarter, the input is a quarter, right? 1/4. 1/4 is 2 to the power of -2. Sorry, -2. And that answer is -2. So when input is quarter, the output is -2. Okay, so that's how we get to these. And next, let's plot these points. Okay, let's plot these points. I'm going to set up the rectangular system in such a way that to the left of y-axis, there's nothing there because those x are less than 0. They're not in the domain. They're not in the domain. Okay. There. I don't need them anymore. So I started the graph, right? So we're going to plot 1, 0, so 1, 0 here, 2, 1. So I'm going to plot these 4 points first. Okay, these 4 points first. We're going to add some points. The first one, of course, 1, 0, right? That's, if we can see it. 2, 1, input 1, output, input 2, output 1, and input 4, output 2, input 8, output 3. So those are the points. Okay, those are the points. You see those points are above x-axis. Now, how about this guy? We're going to plot these two. We're going to do one at a time. 1/2 is the input and the output is -1. There, right here. You see this point? Input is 1/2, output is -1. Okay, we can mark each one of these points. And this one, input 1, output 0, right? And this point, input 4, output 2, Oh, no, sorry. This is 2, 1. Never mind. Okay, my bad. I'm a little ahead of myself. 2, 1. Okay, input 4, output 2, input 8, output 3, right? You can see inputs are all positive. But when the input is smaller than 1, when input is half, the output is negative. Okay, so how about this point? How about this point, right? Input a quarter, input a quarter, output is -2, goes down here, right? So that's the point. I'm going to mark it. Quarter, output -2. So what do we expect for, you can see as X is getting, the input X is from 8, 4, 2, 1, half, quarter, we're getting closer and closer to 0. And the output, look at the output from -1 to -2, and we anticipate for input 1/8, the output is going to be -3. So the output is going down, 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 down. Okay. All right, let's see if that's true. Let's see if that's true. Now let's do, no, sorry. So let's apply the function, right, for 1/8. When the input is 1/8, right? So this is 1/8. 1/8 is 2 to the power of -3. So the output is -3. And the point is going to be 1/8 is the input, and the output is -3. If we plot this point, guess where it's going to be? It's going to be lower, right? It's going to be closer to the y-axis, but lower. There, but never touched it. Remember, if it touches, that means X is 0. X can never be 0. So if we connect all of these dots, right? If we look at the input 1/16, it's going to be even closer. It's going to be even closer to y-axis, but it does not touch it. Does not touch it, because for 16, for 1/16, right, is 2 to the power -4. This is going to be -4. The point is going to be 1/16. The output is a -4. So it's going to be even lower. It's going to be even lower. So in general, what kind of tendency do we see? We see it as input approaching 0, right? Input approaching 0. Okay, I'm going to erase this. Okay, as input approaching 0. Oops. Let me use a different color, please. Okay. When the input is approaching 0 from larger than 0, So here, this is going to be from larger than 0. The output, okay, the output, F inverse of X, which is log base 2x, right? The y value is going to approach, make it red. It's going to approach -infinity. Okay, so this quantity as x approaching 0, getting closer and closer to 0, from larger than 0. So this is going to approach negative infinity. Go down, 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 down infinitely. So that's why the range is from negative infinity. In the other direction, it could get higher and higher, right? As input getting larger and larger. As input getting larger and larger, and the output is getting higher and higher yet. Okay, so this is the graph. So now it's time to connect the dots. So please mark these points before I clean up, because I'm going to connect. Well, I think, let me see if I can connect the dots right now. Okay. Let me do it. Sort of. Okay. So I'm going to connect the dots. Log base 2x. We connect the dots. So as x approaching 0 from larger than 0, it approaches negative infinity. In the other direction, it's obvious when x is approaching, when the input approaches positive infinity, the output is also approaching positive infinity. And this explains why the range for this function is from negative infinity to positive infinity. Okay, so now let's clean up. Okay, let's clean up. So the range, okay, is consistent with what we got from the inverse function perspective, which we did earlier. Okay, when we are trying to find the inverse function from that perspective, it's consistent. Domain and range. So these two are consistent. So from two different angles, we get this kind of consistency. Well, we've been talking about these two functions, right? 2 to the power x and log base 2x. They are inverse function to each other. They're inverse function to each other. Let's see if they are. Okay, we got the graph for log base 2, right? And next, let's graph the other function, 2 to the power of x. We put them in the same picture and make it red. Okay. And of course, I need to adjust the picture. Okay, let's see what this will do. And I'm going to make it higher. There we go. How about that? And I try to make the two about the same, the same proportion. Now, right? Let's look. Now, when you see that these pictures looks like they are going to be symmetrical, they're going to be symmetrical about that interesting line. There, okay? And one's domain is the other's range. One's domain is the other's range. Summarize. Okay, summarize. What are the 3 points that we have, right? Number one, right? 2 to the power, oops. Oh, how did I get that? My bad. Number 1, f of x is 2 to the power x, right? To make sure that we have our assumption in the right place. And its inverse is log base 2x. Log base 2x, right? They're inverse function to each other. Inverse function to each other. Inverse function to each other. They're uniquely corresponding to each other, right? And what is the domain for, you know what? I probably could make a table, right? I should make a table. I think make a table would make it so much easier, right? Let's do the table then. I don't need so many rows, right? So f of x is right here. Its inverse is right there, right? We had the picture. We had the picture. I'm going to put it here, right? And what is the there? That's a 2 to the power x, right? That's 2 to the power x, right? That's 2 to the power x. I just had to make some adjustment to the scale so they look. So I should make this red for that correspondence, right? And this piece, so let's make it a 9 to 9. So I'm making some adjustment to the scale. Okay, so this is 9 to, right? This is to the 9 to. Okay, and this piece, of course, is log base 2x. So I'm going to just put this here and remove the red. Right, remove the red, delete it. There we go. Whew. Why is that? There we go. Sometimes the software can be a little bit temperamental, right? Anyway, so inverse function to each other. The domain for this function is from negative infinity to positive infinity, right? And the domain and the range for the exponential, right? The domain for the range for exponential is positive numbers, 0 to infinity. And one's domain is the other's range. And the domain for, as we've seen from both perspectives, right? The domain for its inverse is the other's range. And the range is all real numbers. And the picture also confirms that, right? The picture also confirms that. And next, let's look at the endpoints. Okay, let's look at the endpoints. So these two rules, right? So as for this piece, as x approaching negative infinity, right? So we have discussed that as x approaching as x is approaching negative infinity, 2 to the power of x, 2 to the power of x, not 2, approaches 0 from larger than 0, right? So that's describing in this direction. Okay, if I'm still picky about the colors, let's change the color, right? To blue as x approaching negative infinity. The curve will get closer and closer to 0, but always above 0 and never touches the x-axis. Okay, so this is a kind of calculus description, but it doesn't hurt for you to know now. Okay, get used to it. In this direction, right, as x approaching 0 from larger than 0, the output is approaching negative infinity. The output is approaching negative infinity, right? Approaching negative infinity. So we're going to write it here in our summary. So as the input, right? This input approaches 0 from larger than 0. The output log base 2 of x, so this is the output, will approach negative infinity. Okay, this is something you'd like to know for your calculus class. And you know, so you can see it's the notation really comes by very naturally. Okay, so this is putting together these two curves. It confirms, right? It confirms one more thing. Okay, one more thing to do. Okay, they're inverse to each other, so that's what we have. Number 2, okay, number 2. Remember the composition we did, right? The composition of functions, right? The composition of functions. They're inverse function to each other. Okay, they each have their own domain and range, right? They each have their own domain and range. We're very clear about it. And the composition, F composite, F inverse of x, and this x should be from the domain of logarithm base 2. So this x, this should equals to x, where x is from the domain of log base 2x, which is 0 to positive infinity. And the other property also works, is F inverse composite with F, right? This time the x is from the domain of F. What is domain of F? All real numbers. So this x, even though they're both called the same name, they are from different interval. In other words, these symbols are mere placeholder. They are mere placeholder, okay? And we can verify this. Verify this, right? For example, the left-hand side on the first one, right? That's equals to F of F inverse of X. F inverse of X, what would that be? It's F, we do it from inside out, right? F inverse X is a log base 2x. Log base 2x. And now the input is log base 2x, so we're going to take it to the 2 to the power, right? So 2 to the power of log base 2x. Guess what this should be equal to? This has to equals to x. This has to equals to x. Okay. And on the other hand, from the definition, we will see the same thing. We will see the same thing, right? Because you can see omega is equals to 2 to the power triangle. Triangle is the same as this guy. So if I replace, right? If I copy this piece, if I copy in this piece and put it here, replacing triangle by its equal, which is on the other side. And that confirms this guy as well. The only difference is one is called omega, one is called x. It makes no difference. The placeholder, excuse me, it's just a placeholder, right? The placeholder omega in the same spot. So let's look at the other one. Okay, so note that this x is from the domain of logarithm, log base 2x. Next, let's look at this piece. Let's look at this piece. On this piece, okay, it equals to F inverse of f of x, okay? F inverse, of course, this x will be from where? It's from the domain of f. The domain of f is all real numbers, okay? And then we have there, right? F inverse, parentheses, replacing f of x by its equal, which is 2 to the power x, right? F inverse is log base 2x. So we're going to do another we're going to apply the rule of the function, right, on 2 to the power x. And that's going to be equals to x. Right? So both are confirmed. To summarize, not only these tables, we completed this table for our summary, and we also have proved and verified these are true as well. And the symmetry, right? Everything about inverse function, the pair of functions that are inverse to each other are true, okay? And thank you for watching. Next time we'll continue on these functions.